Today I want us to look at the power rule, basic rules, product rule, and the quotient rule. And these rules are actually we are actually using them to find the derivative of some function f of x so that we can find f prime of x. So basically, why these rules are more important, you will find out that in most cases, when we are actually using the first principle, there is some more maths that is needed. It's either to simplify, or sometimes we need to know more about limits to actually find derivatives. So these rules are actually trying to eliminate that risk of actually not being able to find a derivative of a function if you are not good with limits. So let us look at each of these rules and see if we would be able to actually find derivatives. And also another thing that is much more important, you'll find out that when you're actually dealing with calculus, most people think that calculus is just math that is studied and need to be studied by mathematicians and people who are so motivated by maths. But if you are playing a closer look to what we are actually doing here, the end goal, we want to be able to actually analyze functions, right? So if you are able to analyze functions, you will be able, if let's say you wanted to analyze some data, use functions to actually analyze that data. And also another thing that is usually more important is that most people who want to venture into data analysis, you might be doing data analysis maybe for just science in general, or you wanted to analyze data in your career, you'll find out that calculus is also one of the tools that you need to be strong in. Of course, if you are good with calculus, linear algebra, stats, and some coding, you are actually good when it comes to analyzing data. So being good with calculus, at least you are eliminating one of the things that you need to be good at. Without further ado, let's just focus on this a power rule, basic rules, product rules, and quotient rule. Let's start by the derivative of a constant function. So if let's say suppose that we have some f of x equal to c, where c is a constant, and this one is can be negative, it can be positive, it can be a fraction, it can be a decimal, it can be a root, as long as this one is a constant, then the derivative, or f prime of x of this particular function, is always going to be a 0. So if let's say we are using Leibniz notation, you know that the derivative is always going to be dx. This x here is just saying that the variable that we're using, or the independent variable in this function, is x, and then this one is just telling us that we wanted to take the derivative of whatever that function is. So this function is going to be c. So a derivative of a constant is always going to be a 0. So if let's say you had a function f of x is equal to 5, you know that f prime of x is supposed to be equal to a 0. Or if this one here is just equal to pi is a constant, then f prime of x is going to be a 0. And if f of x is equal to e, of course we have the same thing. What did this actually mean? If you remember, when we were finding f prime of x is actually the slope of the tangent line touching this curve at x, at this value x here. So the meaning of having a 0 here, we just say, let me write it down. The meaning of this is that the slope, not slope, the slope or the gradient of the tangent line touching the curve f at point x is 0. So the slope is actually 0. What that is supposed to mean, it means that the function is not changing. Is not changing, so it is constant. So that's what we actually mean by. So every time you have a constant function, you must know its derivative is actually 0. And now let us talk about the power rule. What do we mean by the power rule of derivatives? This is saying that if n is a real number, so what this means, n can be negative, can be positive, n can be 0, and n can be a decimal, or n can be a root. So if n is a real number and we have f of x is a power function. In other words, f of x is equal to x to some power n. Right? Remember that n can be negative, it can be anything. Then the slope of the tangent line that is touching this curve at point x here is going to be given by f prime of x. We get it by we take this n here, we bring it down, so we have an n here, and you multiply by x, and then we subtract 1 from the exponent there. So that's all you have to do. Bring the exponent down, and then you subtract a 1 from it. That's what we do. Let's take some examples here. So these are the nice examples that we actually have here. So we have, let me say we have a, and our a is, we have f of x is equal to x to the power 5, and then we have b here, and our b is going to be f of x is equal to 1 over x squared, and then our c here, we have f of x, and our f of x is equal to square root of x. So what is basically important here is one thing here is that this thing is saying that go to the exponent. So this is our exponent. So we're actually gonna say f prime of x is going to be, we bring the exponent down, so we're going to have 5 times x raised to 5, and then we subtract a 1 there, and then we can just simplify. We have 5 times x to the power 4. So this one is the slope of the tangent line that is touching this particular curve at point x. And of course, if we are specific about that point, let's say x is equal to 1, we can always just plug in 1 here, and we get the exact slope or that we are looking for. And then for this one here, what you need to notice here is that we want the x to the power. We don't have a denominator here. The denominator is 1. So we don't want it to end up with a fraction of this kind here. We want it to have x raised to the power. So we want to make sure that what we're actually having here, we have a power function. So we first have to change this function here to be, we have a 2 here, and now 1 over 2 is just saying that we have x raised to minus a 2. So now we have a power function here, x raised to something here, and then this simply means now our f prime of x is just going to be, you bring the exponent down, so we're going to end up having minus 2 times x raised to minus 2, and then we subtract a 1, so we're going to subtract a 1 here, and then of course we will end up having something like minus 2 times x raised to minus 2 minus 1 is going to be a minus 3. Of course, this is the final answer, but if the answer was given in this fractional form, then your final answer need to be written in the same form that it was given here. So it is not complete to just leave it like this. So we have to, if we have a minus, you must know that that part that have a minus is going to a denominator, so we'll end up having a 2 divided by x cubed. I know that some people might end up penalizing you maybe some 0.5 of a mark if you leave it like this, because they give you a function in a fractional form, so they want it back in a fractional form. Others might not, but this and this is the same thing. It shouldn't be that much of a problem. And then of course, when we're actually finding out this one, you will find out actually that this is actually the same as the square root, is just the same because we have a 1 there. It's just the same as x raised to 1 over 2. And then because this power rule, we can only use it if we have x raised to the power, not when we have a square root. So we change that to be this. And then of course now f prime of x is just going to be, we bring this exponent down, 1 over 2 times x raised to 1 over 2, and then we subtract this one here. So we're going to end up minusing a 1. So once we have that, now you can finally see that technically this one thing is just going to be 1 over 2 times x raised to, so we have 1 over 2 minus 1. So I am subtracting a big thing from a small thing. Of course, I will end up with a minus there. And then if I look into this, I have something that is full, and then I'm taking out half of it, so I will be left with half. Or there is half missing here to match this. That is why we have a half. And then this whole thing now will be, because I gave you this in terms of square root, so I want you to rewrite this in terms of square root. First of all, I have a minus exponent there, so which means that if this thing is a minus, it needs to go into the denominator. So I end up having 2 times x raised to 1 over 2. And of course, we were given this in a root form, so we rewrite it as 2 times, you know that x to the power 1 over 2 is the same as root x. Of course, try and make sure that you match what is given here. Most people are very strict when it comes to marking. If they give you in this form, they want your final answer in that form. So you might end up finding yourself losing 0.5 of a mark. Others might even take out 1 mark. So it depends. It depends on how strict the person is. So hopefully now you are actually getting how to find the derivative or the slope of the tangent line that is touching this curve, whereby the curve is actually characterized by a power function. Also, another thing will be, if let's say I give you f of x is equal to x raised to the square root of 2. You know that this is just a constant and it is a real number. This simply means now f prime of x is just going to be, you bring the exponent down, and then of course you have the root of 2, and then you subtract a 1. Of course, that will be your slope or your derivative. That's it. That's what is important about this whole thing here. Now, let us look at the constant multiple rule. Let me write it down here, black. You have a constant multiple rule, right? If C is a constant, so C can be negative, can be positive, can be a real number, decimal, rational, a fraction. Is just a number. And F is a differentiable function, right? Then if let's say I wanted to find, let's say I'm given some h of x, and h of x is equal to c times f of x. Then to find h prime of x, this is just, I have to take the derivative with respect to x. Remember, there is x here, so I'm taking the derivative with respect to x of c times f of x. So if I have a constant in multiplying a function, I can always bring the constant out. So I have a constant times the derivative with respect to x of that particular function here. In other words, this is just going to be the same as c times f prime of x. So that constant, I can just take the derivative of this function, and then after taking the derivative of this function, I just multiply by that constant. That's what this thing is actually saying. And of course, we can have some examples. One example would be, suppose I have f of x and okay, because I was using f of x here, let me say, suppose I'm actually having my h of x, and my h of x is equal to 5x to the power 4. And then if I am looking for h prime of x, all I need to do, I need to take out this 5 and leave as it is, and then take the derivative with respect to x of x to the power 4. That's what this thing is actually saying here, which means now, because you can see that is x raised to a power here, so all I need to do to take the derivative of this, I just need to bring the exponent down, so I will end up having a 4, and then I multiply by x, and then I have a 4, and then I subtract a 1 there, and then 5 times 4, we know that it is 20, and then we end up having x, and then 5 minus 4 minus 1 is going to be a 3. So the derivative of this, and of course you can pull that one out. And then another one will be, if I have h of x is equal to 1 divided by 2 root x, and you want to find the derivative of this, and the question usually says find h prime of x, or you can say find the slope of the tangent line touching this particular curve at point x. If it's not x, they will give you the point maybe at x is equal to 5 or x is equal to 2. Now, how do we end up dealing with this? Remember that what we are actually dealing with here, we wanted to have a constant multiplying a function here. So here I have a constant divided by another function, so I need to first rewrite this whole thing so that it looks like a constant times a function. So if you look carefully into this, you will find out actually our h of x is just the same as something of this nature here. First of all, I don't want this root when I wanted to find a derivative. Let's first fix that, and then we will deal with it at a later stage. So we have a 2 times x raised to 1 over 2, and then of course if this is in the denominator and I want it to be in the numerator, it will end up being 1 times x raised to, because it was in the denominator, I just have to minus write the exponent with a negative sign, and then all over a 2. And if you look into this thing here, this is just the same as I have this constant here as 1 over 2 times x raised to minus 1 over 2, and now I need to find nicely my derivative is going to be, the constant is always gonna be there because I can always pull out the constant, and then I multiply this by the derivative with respect to the variable that we have here, which is x. So here we're gonna end up having minus x over 2, and then of course I will have 1 over 2 times, I bring this exponent down, which was minus 1 over 2 times x raised to minus 1 over 2 minus 1, because I still have to subtract 1 from the exponent. And if you look carefully into this, you will find out that I have 1 times minus 1 is just going to be minus 1, and then divide, and then I have 2 times 2 is going to be a 4 here, and then times x. Now I have minus 1 over 2 minus 1 over minus 1. So minus and a minus, I know that I will end up having a minus here, and then of course here, if I have 1 over 2 and then I have 1 here, I wanted to end up having the common denominator here so that I can add nicely. So how do I end up finding the common denominator? This one, the denominator of it is 1, here the denominator is 2. In order for me to get a 2 here, I just need to realize that 1 is the same as 2 over 2, because I want to have a 2 that is there in the denominator. So here I end up having a 2 in the denominator, so I have a 2, and then 2 divided by 2, 2 divided by 2 is just 2 times minus 1 is going to be a minus 1. So I end up having here um I'm going to end up having a -1 here. The reason I'm being hesitant here is that I've already placed that minus there. Let me just say this here. I'm just gonna do it here. I have -1 over 2, -2 over 2. The common denominator is 2, and then of course 2 divided by 2 is 1. 1 times -1 is going to be -1. 2 divided by 2 is 1. 1 times -2 is still going to be -2. And then I have -1 -2, which is the same as just -3 over a 2. So this minus here is just saying that I will end up having a -3 over a 2. And now if you look carefully into this, you will actually find out that, of course, this thing here, we were given it in a root, so we want it written in a root, right? So the first thing, when you have a negative exponent, it means that this thing is in the denominator. So I end up having -1 divided by 4 times x raised to 3 over 2. You can see now the exponent is actually positive. And then if you look carefully into this, you know that whenever you have the nth root of a to the power m, this is the same as a. This one is always going to be above, and then in the denominator we'll end up having an n. So this one that was outside is the one that is in the denominator. So when I have something in the denominator, I know that it is outside. So here I will end up having -1 divided by 4 times I have x. So this one in the denominator is supposed to be outside the root. We usually place it 2, or we cannot place it. It doesn't matter at all. So we end up having a 3 there. So that's how this whole thing is actual to be. I can just say therefore h prime of x is just going to be -1 over 4 square root of x squared. No, x cube. That's what is actually important here. Now I want us to talk about the sum rule. So the sum rule is saying this. Let me write it and see. The sum rule is just saying if f and g are both differentiable, not dogs, functions, are both differentiable functions, then if, let's say, I want to find the derivative with respect to x of f of x plus g of x, I am always gonna get I can always get the same thing by just taking the derivative with respect to x of f of x, and then I add to it the derivative with respect to x of g of x. In other words, it's just that if I can just find the derivative, rewriting it in this form is going to be the same thing like this. And of course, I can just take, if I want the derivative of the sum of the two, I can just take the derivative of this and the derivative of this, and then I sum them up. And if I wanted to find, let me say this one is the difference, the difference rule. So if both f and g are differentiable functions, then the derivative, so the derivative with respect to x of f of x plus minus g of x, I can always accomplish this by just taking the derivative with respect to x of f of x, and then take that derivative and subtract the derivative with respect to x of g of x. No, this is just g of x. Why am I writing something that is not correct? So g of x is Rewriting it, we just end up having f prime of x minus g prime of x. This is g prime of x. Let's take some examples and see if we can actually get the gist of what is actually happening here. These are just examples. Let me give you one example or two here. Suppose the question is saying find the formula of f prime of x, or just f prime of x, or the slope of the tangent line touching the curve f. Find the formula f prime of each of the following. So the question will be either be find the slope of the tangent line touching the curve f at point x, or find the formula of this, or find the derivative of this particular function, whereby I have my a here, which is going to be my f of x is just equal to 2 times x squared plus x, and then my b is going to be my f of x, which is equal to x cubed minus x squared, and then the last one is going to be I have my f of x is equal to pi times x to the power 5, and then plus e times x raised to the square root 2, and then minus a 6x. So of course this is not going to be hard, because our f prime of x is just going to say that I'm gonna take the derivative of this, because if I want to find the derivative of this particular part here, this is a constant, I can always pull it out. So taking the derivative with respect to x of 2x squared plus x is going to be not hard, because I can pull out this constant and then take the derivative of this and the derivative of that. I take the exponent down, I'm gonna have a 2 here, and then have x, and then there's not enough space here. So what I'm going to do here to make sure that I open some space, I am just going to use this nice tool here and push these things a little bit down, so that I can get a space, and then I can go back there. So I want to find f prime of x, and f prime of course is going to be d dx of 2x squared plus x, and then of course according to the rules above, the sum rule, I can always just take d dx of the first function, which is 2x squared, and then I sum it with d dx of the second one, which is just x there. And I'm still gonna push this because I seem to need some space here. And then of course this is going to be equal to, if I take this one here, this constant I can always pull it in front, so I will have 2 times d dx of x squared, and then plus, and then what is the derivative of this? Take note that there is a 1 there, so if there is a 1 up there, I can always bring the 1 in front and then have my x, because there was a 1 there, and then I subtract a 1. So this is going to be, I do the same thing here, I still have the 2, which was that 2 outside, but to get a derivative of this, I bring the 2 down, and then I multiply x, and then I have a 2 minus 1 there, and then this one here is just going to be 1 times x raised to 0. And if you look carefully into this, you'll find out 2 times 2 is going to be a 4, and then times x, which is this x, 2 minus 1 is just going to be a 1, and then here x to the power 0, we know that x to the power 0 is just going to be a 1, so we end up having a 1 here. So the derivative of this is going to be 4x plus 1. Simple. Now let us find the derivative of this one here. The derivative of this here is very simple. What did I do? Yeah. To find the derivative of this, is very simple. I want f prime of x, and of course first I'm going to take the derivative of this part here, which is going to be d dx of x cube, and then plus, because we have a minus, so we're going to have a minus d dx of x squared. And of course you know that I can just bring in 3 down times x, and then I'm going to have 3 minus 1, and then minus, and then here I'm going to bring it 2 down, and then I'm going to have x raised to 2 minus 1, which is just going to be simple as 3x squared minus 2 times x. That's how simple this thing is, that you can just bring this one down. And then it's always easy for someone to just assume that no, I can just do this in my head. My advice is always do it and clearly show it for your own good, because even here in this particular case here, you might find yourself just saying, this one is going to be 2x, and end up having here a 2x. You forget to bring the 2 down because you're seeing a 2 and a 2 there, and you think you already brought it down, and you forget to bring this 2 down because this 2 is always pulled out. So always write everything down so that you don't make a mistake. Let's look into this one here. F prime of x of course is going to be the simple. This one here is a constant, so I can always just leave as it is, and then take the derivative of this part here. So to take the derivative of this, I need to bring the exponent down. So I'm going to have a 5 times x, and I have a 5 minus 1. And then here, e is a constant, so I am going to just leave it as it is. I'm pulling it out, and then I bring the exponent down. So I will end up having the square root of 2 times x raised to the exponent 2, and then I have to subtract a 1 there, and then minus, of course, the derivative of this is just going to be 6, and then when I'm bringing, remember there is a 1 there, when I'm bringing in a 1 there, and then I will end up having x raised to 1, which was that 1, and then I have to subtract a 1. The final answer is going to be simple here. 5 times pi is going to be 5 pi, and then you have x raised to 4, because 5 minus 1 is 4, plus square root 2 e. I can start with e or square root, is still fine, and then I'm still gonna have x, because this one cannot be just simplified without a calculator, so I'm gonna leave it as it is, and then minus 6 times 1 is just 6, and then x raised to 1 minus 1 is going to be x raised to 0, which is just the same as 1. So this is actually your final answer. Don't get so confused because of these constants here. What is important is that it is a constant, so I can always pull it out of the derivative sign, and then I can take the derivative of this power function as easy as I know how. Now let us talk about one of the important things now, which is the product rule. So what is the product rule is actually saying here is that if both f and g are differentiable functions, right, they are both differentiable functions, then if I wanted to find the derivative with respect to x of the product of these two functions, there is the easiest way to do it other than just using the first principle. Just after you have studied these rules, you will find out that you will tend to neglect the first principle. So in most cases, the question will specify that they want the first principle. So this one is the shortcut of finding the derivative of the product of two functions. And this one is very simple, that you keep one function. I'm going to keep this second function, g of x, and then I'm going to take the derivative of the first function. The derivative with respect to x of the first function. And then, of course, I add, and then I'm going to keep the first function, f of x, and then I'm going to take the derivative of the second function. That's how this thing is, how easy this thing is. So this is the same as g of x times the derivative of this, we usually rewrite it as f prime of x plus, and then here we actually have f prime of x times g prime of x. So basically here what is important is that you need to take, when you are taking the derivative of this function, this one you keep it as it is, like this. You take the derivative of this one and then you add. You can see that when I'm taking the derivative of this, g of x is kept as it is, and then when we're actually taking and then we add, when we are taking the derivative of this one here, this one is kept untouched, so we keep it as it is, and then we take the derivative of the second function. Let us take some examples here. I'm gonna take some examples here. So one example will be something of this nature here. Let's say that I'm gonna give you, let's say 2. Yeah, let me give you 2. So we have f of x is equal to this is not how this thing is. I'm gonna say this, find f prime of x of each of the following functions. Right, so my a is going to be, let's say f of x is equal to x squared and then square root x times square root of x, and then my b is going to be f of x is going to be equal to x squared plus 2x, and then I have to multiply this by x squared plus square root of x. I can give you maybe a bonus one here and say I have f of x is equal to, I have x cubed plus 2x squared plus x plus 7, and then I'm multiplying this whole thing by 5x to the power 6 plus x to the power 5 plus x to the power 4 plus 2x squared. I have something of this nature. And now I want us to actually find the solutions of these particular functions here. So truthfully speaking here, you can run away from using the product rule here and just say that this is the same as just x squared times x raised to 1 over 2, and then you can just say that this one is just going to be the same as x raised to 2 plus 1 over 2, and then you change this 2 here to be 4 over 2 so that we have the common denominator, and then you say that this function here is the same as x raised to 5. 4 plus 1 is going to be 5 over 2. And then of course, if you want to find a f prime of x, you can just say that I'm going to bring in a 5 down, 5 over 2 down, and then I'm going to have x raised to 5 over 2, and I'm going to subtract a 1 here. And then of course you can see that this one here is just the same as 2 over 2 if you want to have a common denominator, and then this is going to be the same as 5 over 2 times x raised to 5 minus 2 is going to be 3 over 2 here, which is just something of this nature here. We have 5 over 2 times the square root of x cubed. So you can run away when you're finding this derivative here to be something, the derivative of this function, by first simplifying it and then using the power rule. But I don't want us to use the power rule here. I want us to actually use the product rule, because you can see that I have one function here and I also have another function being multiplied together. So this one here I am going to call it h of x, and this one here I am going to call it g of x. And if you look carefully now, f prime of x is just going to be, if I am taking the derivative of this one, I'm going to keep that one here. I know that I need to have g of x times h prime of x, and then because there is a product I have a plus, and then I'm going to keep h of x, and then I'm going to take the derivative of g of x. That's how the product rule is saying. And then if you look carefully here, our g of x was the square root of x. So we have the square root of x, and then here the derivative of the first one, so it's going to be d dx of x squared. And then of course I come to this one here, h of x, we keep it as it is. It's going to be our x squared there, so we have x squared, and then g prime of x is just the derivative of this one, so I will end up having d dx of the square root of x. And then we can try now and simplify and see what we're actually getting. We still have the square root of x, and then here, what is actually the derivative of this power function here? You bring an exponent down, and then you are left with x, and then you subtract a 1 in the exponent. And then, of course, plus x squared. And then if you look into this here, this one, we still need to fix it so that it actually looks like that of a power function. And then root of x is the same as x raised to 1 over a 2. And then we can continue here and notice that we have a 2, so we end up having a 2 times root of x. I'm also going to change this root of x here to be the same as x raised to 1 over 2, and then times x here. Take note that if I have 2 minus 1, 2 minus 1 is just 1 there, and then plus x squared. And then what is the derivative of this? The derivative of this, I bring the exponent down as it is, and then I multiply by x, and then in the numerator there, I will end up having, in the exponent, I'll end up having 1 over 2, and I subtract a 1. And then after subtracting a 1 here, you can see that I will end up having 2 times x raised to 1 over 2. When multiplying powers of the same base, you add the exponent, so I end up having 1 over 2 plus 1. And then here I will still going to have 1 over 2 times x squared, and then times x raised to. And if you look carefully in what is happening here in the at what is happening here in the exponent, we are actually having half minus 1. Half minus 1 is the same as half minus 2 over 2. So this is what is basically happening here. 1 minus 2 is going to be minus 1 over a 2. And then of course we can proceed here. If I actually have 1 and I wanted to have a 2, I know that 1 is the same as 2 over 2. So 1 plus 2 is going to be, I still have that 2 here, x. 1 plus 2 is going to be a 3 there. And then I take one denominator, which is a 2. And then when it comes to this one here, I end up seeing that actually I still have 1 over 2. And then I have this one here is going to be x raised to 2. Multiplying powers of the same base, you add the exponent, minus 1 over 2. So 2 is the same as 4 over 2. And then if you notice here, I end up having something that is very nice, which is just simply as I have 2 times x raised to 3 over 2. And then here I have 1 over 2. And then here you will see that 4 minus 1, I still have x. 4 minus 1 is going to be 3, and then the denominator is common. We have 2 and 2, so I have a 2 there. And now I have x raised to 1 over 2, 3 over 2, and I have x raised to 3 over 2, which is something that is actually common. I have x raised to 3 over 2, and then if I take it out, I'll be left with a 2, plus taking this one out, I'm left with 1 over 2. Right. And if you look into this one here, you will find out actually this piece here is just the same as 2 is just the same as 4 over 2. And then 4 plus 1 is going to be 5. And then I take the common denominator, which is 2. And then I have x raised to 3 over a 2. Take note of this answer here. Is saying that our f prime of x is equal to that, which means the slope of the tangent line touching the curve f at point x is given by this. So if you want to find out what is that at x is equal to 1, you can just plug in x is equal to 1 there, and you can see that this is actually the same as this one here. But take note that this question, it was given with a root. So because of course it was given with a root and also x squared, so it's still fine to just leave it like this. It's still fine, but you can proceed further. I don't think there's a penalty here because this one was given with the root, and also the other exponent was not in a root, and the other x was not in a root. So this is the final answer, or you can rewrite it to be 5 over 2 times the square root of x squared x cubed. So that's how you can actually, this is not approximation, this is just equal to. And then the second solution, which was B, we actually ended up having something that is very nice, as we had this thing here. I am just gonna copy it. Sorry, I'll just copy it as it is, and then I'm just gonna copy it, control copy, and then I'm gonna paste it here. So this was our B. So how do we find f prime? Our f prime is just going to be f prime of x. We're just gonna keep this as it is, so we have x squared plus square root of x, and then times the derivative with respect to x of this bracket here, which is going to be x squared plus 2x. Take note of this here. This one here, we take it as one function. This is going to be our function, and then this one also is going to be our another function. So this is going to be our h of x, and this one is going to be our g of x. So we keep our g of x, this is our g of x, and we take the derivative of the first one. And then secondly, we add, and then we keep our h of x, which is going to be x squared plus 2x, and then we take the derivative of g of x with respect to x. So we have x squared plus the square root of x, right? And then once we do that, you will find out that this one will stay as it is, plus the square root of x, and then now we take the derivative of this. When we are taking the derivative of this, we're going to take the derivative of this and take the derivative of that. So the derivative of this, you can see that this is a power function, so you bring a 2 down, we're going to have a 2 times x, and then we subtract a 1 there, we're still going to have a 1 there, and then plus. Here we take the constant out, so 2 will still gonna stay there, and then we bring a 1 down, so we're gonna multiply by 1, and then we have x. The derivative of this is going to be 2 times 1 times x. Since we have a 1 there, when we're subtracting a 1, we'll end up having 2 times x, because 2 times 1 is just 2, and then we have x to the power 0, and x to the power 0 is just a 1. So we'll end up having a nice thing like this one. Let's come to this one. We're still gonna have x squared plus 2x, right? X squared plus 2x, and then the derivative of this, of course, we bring the exponent down here, we're gonna end up having a 2, and then times an x, because when we're subtracting a 1 in the exponent, we'll end up being with just a 1. So that's what we have here, plus. What is the derivative of this? First of all, we know that the square root of x is the same as x to the power 1 over 2. So we bring the exponent down, it's going to be 1 over 2 times x raised to I'll end up having here an x raised to 1 over 2, and then I subtract a 1. So when we are subtracting a 1 here, I mean, we have done the derivative of this. We shouldn't be worried much because we're supposed to end up with 1 over 2 here. Now, this is actually the final answer. The reason I'm saying this is actually the final answer is because there's nothing common here between this one and that one. There's no common. There's nothing common in this factor, and there's no common factor in each in these brackets. So we can just leave it like that. There's nothing much more important unless you wanted to leave this part with a square root as it was given. Then we can actually have x squared plus square root of x, and then we end up having that 2x plus 2, and then we're still gonna have a plus here, and then we're gonna have x squared plus 2x, and then here we're still gonna have 2x plus, and then in this particular equation here you'll find out that this part here we have a negative, which means it goes to the denominator there, so you're gonna end up having 2 times x raised to 1 over 2. Now it's positive but in the denominator because of the sign, and then 1 over 2 is still the same as just the square root. So this is actually your final answer. Just a quick summary here. We had our f of x, which was equal to h of x times g of x. So our f prime of x was simply equal to h prime of x. We keep this one here as it is, and then we take the derivative of the first, and then plus we keep the first one, which is h of x, and then we take the derivative of the second. So in the given function here, our h of x was this one, and then our g of x was this one. So we take the derivative of this. Yes, I was a little bit faster because at least now you have an idea. You know how to take the derivative of this. You know how to take the derivative of this. You know how to take the derivative of this on each of these ones. That is why we end up getting something of this kind. The last example was, I will try and be as slow as possible because it seems a little bit mathematically involved. So this was the last example that we had. I'm gonna copy, and then I'm gonna place it somewhere here. Let me move it up so we have that one. So like I said, the first thing that you actually do here is very simple. You identify that these two functions are just being multiplied together, and this first one here we're gonna call it h of x, and then this one we're gonna call it g of x. And then if you look carefully into this, so f prime of x is going to say that I am going to keep g of x as it is, and then I'm going to take the derivative of h, and then plus I'm keeping h as it is, and then I multiply by the derivative of g of x. Now what is actually g of x? G of x is that whole thing there, so we actually end up having 5x to the power 6 plus x to the power 5 plus x to the power 4 plus 2x squared, and then I take the derivative with respect to x of h, so I'm gonna take x cubed plus 2x squared plus x plus 7, and then I'm gonna leave h of x as it is, so I'm gonna have x cubed plus 2x squared plus x plus 7, and then I take the derivative with respect to x of I kept this one as it is, and now I'm taking the derivative of that, so we'll have 5x to the power 6 plus x to the power 5 plus x to the power 4 plus 2x squared. Now it's all about simplification. This one was kept as it is, so I had 5x to the power 6 plus x to the power 5 plus x to the power 4 plus 2x squared, and then now what is this derivative? I'm gonna bring a 3 down, so I'm gonna end up having 3x. I'm subtracting a 1, I'll end up having a 2 there, plus when I'm bringing this 2 down, it will multiply with this 2, so I'll end up having a 4, and then I have an x there, and then this 2 I'm subtracting a 1, so I'll end up having a 1 plus, and then this one I have a 1 here, so I bring the 1 down, and then when I'm separating a 1, I will end up having x raised to 1 minus 1, which is 0. So I will have x raised to 0, which is just a 1. So I leave it like that. And then the derivative of a constant is always 0. So this one, its derivative will be 0. And then I leave x cubed as it is, plus 2x squared plus x plus a 7. And then I take the derivative of this. I bring the 6 down. When I'm bringing the 6 down, it will multiply with this 5 and will end up having a 30 times x. And then I subtract a 1 in a 6, I will end up having a 5. Plus, I bring a 5 down. There is nothing there, so it's going to be alone. And then I have x. I subtract a 1 there, I will end up having a 4. Plus, I bring the 4 down there, I will have a 4. I have an x, and then I subtract a 1 there, I will end up having a 3. Plus, I bring this 2 down, but there is a 2 there, so I have to multiply 2 and that 2, I'll end up having a 4, and then I'm going to have an x, and then I'm subtracting a 1 there, I'll still have a 1, and then that's it. Of course, if you look into this, you can see that there is not much of a common factor, so we can leave it like that. Even if you expand, it will expand and it will become so much biggest polynomial that you have. So the reason I was taking this kind of an example, I wanted to show you that not every time you can always expand and then take the derivative. Sometimes expanding, because now in order for you to expand, you have to take this, multiply it with that, and then take this, multiply with that, and then take this, multiply with that, and then this, multiply with that, and then you go to the second one. You do the same thing, you go to this one, you end up getting something that is so big that you could have avoided by just taking the derivative of the first, keep the second, and then take the derivative of the second and keep the first. That's how you actually take the derivative using the product rule. Now, let us talk about the quotient rule. What I want you to actually be more focused on here is this. Usually, I'm gonna write this up there so that you actually don't end up making the same mistakes most people are actually making. We have L'Hopital's rule. Right. So once we do the quotient rule, make sure that you understand it. And once we do the L'Hopital's rule, make sure that you understand it. Most students usually confuse these two and interchange them. They kind of look similar to each other. I don't want you to make a mistake. Make sure that you understand what the quotient rule is saying, and you understand what is the L'Hopital's rule is actually saying, and make sure that you don't make the mistake that they're actually making. It's easy to make that mistake. That is why I wanted to specify this up front so that you don't end up making that mistake. What is the L'Hopital's rule is saying? If both f and g are differentiable functions, they might be functions, right? Then the derivative with respect to x of f of x divided by g of x can always be found by doing the following. You take the denominator as it is, right? And then you multiply it by the derivative of the numerator, f of x, and then you subtract. Whenever you have a fraction, you must know that you subtract, and then you keep the numerator as it is, and then you take the derivative of the denominator, and then you divide by the denominator squared. Let me rewrite this. When we're using Leibniz notation, this looks like this. But when we are actually using the other notation, the prime notation, you'll find out that we will end up having, just like we were doing with the product rule, you keep the second, but here our second is the denominator. So you keep the denominator as it is, and then you take the derivative of the numerator, and then you subtract. You keep the numerator as it is, and then you take the derivative of the denominator. But now we have a negative in front, in the middle, and then you divide by the denominator squared. These things can actually be proved, but what is important here is that we don't want to prove these things, we want to use them. Another way to remember this, for me, to make sure that I don't forget, I usually say that I have load high minus high d low divided by low. So what is actually saying, low, you keep the denominator, take the derivative of the high, this is not the height, take the derivative of the one that is in the numerator, and then keep the numerator, take the derivative of the denominator. So this is how I usually do it. Low d high minus high d low divided by low. So that's also another way to look into this particular example. So you can use it, you cannot use it, but that's actually up to you. Let's take just 3 examples, and then there's something else that I wanted to actually give you as a bonus, and then after that I will be able to say, let's call it a day. So let's take some examples here. So the examples are just saying here, find f prime of x for each of the following. Right, so if we wanted to find f prime of x, let me first give you these examples, write them up front. I have f of x, which is equal to 1 divided by x squared, and then b, I'm not gonna write b here, I'm gonna write my b somewhere here. Our b is going to be f of x is equal to square root of x divided by x squared, and then I'm gonna leave some space here and write our c here. C is going to be f of x is equal to x squared plus square root of x all over, I'm gonna end up having x squared plus 2x. Yeah, we'll end up having these 3. Let us try and see if we can solve them. If you notice here, this one is still the same as just x raised to minus 2. I have a minus, which means that it was in the denominator. Times 1 is just still the same thing. So if I wanted to take the derivative of this would simply means that f prime of x is just gonna be minus 2 times x raised to minus 2 minus 1, which is just going to be minus 2x raised to minus 3, or just minus 2 because it's negative, it means it should be in the denominator. So we should be having something of this nature. But we wanted to use, this is x raised to 3. I want to use the quotient rule. The quotient rule is saying I have this whole thing here. So I am going to say this function here is going to be this one here, I'm going to call it h of x. So h of x, my h of x is going to be equal to 1, and then my g of x is going to be x squared. So just for us to notice, this is 1, this one is going to be an x squared. What is the quotient rule saying? Our f prime of x is going to be the same as low d high. So low, we're gonna take this, low means the denominator, we're gonna keep g as it is, or let me first write it like this. So I will end up having g of x, and then times the derivative of the numerator, which is h prime of x minus, and then I'm gonna keep the numerator as it is, and then multiply by the derivative of the new denominator, which is g prime of x, and then I'm gonna divide this whole thing by g of x whole squared. Low d high minus high d low divided by low low. So this whole thing is going to say, what is our g of x? Our g of x is going to be x squared times d dx, or the derivative of our h of x. H of x was 1 minus, and then I'm gonna keep h of x as it is, which was 1 times d dx of what was the denominator. It was x squared, and then I'm going to divide this whole thing by the denominator squared. So I had x squared, this whole thing I'm squaring it up, and then now that I have that, I can say that first, let me move this a little bit. I want to solve this one here. So here, what is a derivative of a constant? A derivative of a constant is always 0. So I have x squared times 0 minus 1 times the derivative of a power function. I bring the exponent down, multiply by x, subtract 1 from the exponent, and then I divide this whole thing by x squared all raised to 2. So whenever I have 2 powers, a power of a power, I can just multiply these, so we'll end up having x to the power 4. And of course, this is the same as x squared times 0 is just gonna be 0, so this one goes to 0. And then this one, 2 times minus 1 times 2 is going to be minus 2 times x. And then here I have 2 minus 1 is just gonna be a 1 there. And then I divide this whole thing by x to the power 4. When multiplying powers of the same base, when dividing powers of the same base, subtract exponent, or I can just cancel one of these x and cancel one of them. I'm left with a 3. So I will end up having a minus 2 over x raised to a 3. So using the quotient rule, I still get the same answer as this. Of course, when you had something like this, it's always easy to use the product rule. I wanted to show you that actually the quotient rule can actually give us the same answer as we did. But for this one, it's actually not it's not being smart to actually use the quotient rule to find this. But when we're actually going to more advanced problems, even here you can notice that actually I can just change this to 1 over the power, change this to x raised to 1 over 2, and then subtract the exponent and use the power rule. But I don't want us to do that. I want us to get used to the quotient rule board, because there are some questions that are coming up that requires the understanding of the power rule. So here I'm gonna call this one h of x, and then this one here I'm gonna call it g of x. I know that to get f prime of x, I know this is just saying low d high, which means I'm gonna take low means the denominator, so I have x squared d dx low d high. What is high is square root of x, which is the same as 1 over 2, and then minus low d high minus high d low. So here I will keep the numerator as it is, which is the square root of x, and then time d low, so the derivative of the numerator, and then I divide this whole thing by the denominator squared, which is x squared squared. What is the derivative of this? We still have x squared. The derivative of this, you bring the exponent down and then you subtract a 1 from it. So I have 1 over 2 minus 1, and then minus the square root of x. We know that the square root of x is just going to be the same as just x raised to 1 over 2, and then the derivative of this, you bring the exponent down and then you subtract 1 from the exponent, divide by x, you multiply these two, so you have a 4. So this is not hard. It's actually very easy. I am going to take this here. I am going to cut it so that I can paste it somewhere here. I'm gonna paste it somewhere down there so that I can gain some space. And of course here I am going to say, I'm trying to simplify here, I have 1 over 2 times x squared, and then this one here is going to be x raised to minus 1 over 2. How is that possible? Is because 1 is the same as 2 over 2. So 1 minus 2 is going to be minus 1, and then I take the common denominator as 2. And then minus, here I still have a 2 in front, and I'm going to have x raised to 1 over 2 times x. 2 minus 1 is just a 1, and then I divide this whole thing by x raised to 4, and then our answer is going to be, I still have 1 over 2 x. Multiplying powers of the same base, you add exponent, so I have 2 minus 1 over 2, because this is minus, so adding a minus the same as just subtracting. 2 is the same, okay, let me continue here. I have let me not write it here, I'm not gonna get enough space. So here I will have 1 over 2, which is this 1 over 2 times x. I have this 2 there, and then plus minus 1 over 2, which is just the same as minus 1 over 2. And then I have minus 2. I have x raised to 1 over 2 plus a 1. So I'm adding this one and that one because x and x are the same. I divide it by x to the power 4. And then of course, if I continue here, I will end up having something that is so nice. Nice as 1 over 2 x raised to x raised to 2 is the same as 4 over 2 because I want to gain the common denominator. 4 minus 1 is going to be 3 over 2, where 2 is the common denominator. And then the same thing here, I'm going to do the same thing. 1 is the same as 2 over 2, so that I can get the common denominator 2. 1 plus 2 is going to be 3, so I still have minus 2. X raised to 3 over, the common denominator is just 2, all over x to the power 4. And of course, this is going to be like, you can see now that I have 1 over 2. I have x raised to 3 over 2, which is common from this term and that term. And then once I take it out, I'll be left with 1 over 2 minus. And then if I take this thing here, I will be taking this, and now I have a 2. And then divide this whole thing by x to the power 4. And if you look here, 2 is the same as 4 over 2. So 1 minus 4 is just going to be actually 3 over 2. So here 1 minus 3 is going to be minus 3. So we have minus 3 over a 2. And then in the numerator we'll end up having x raised to 3 over 2. And then in the denominator I have x raised to minus 4, because now I'm making this in the numerator, so it has a negative exponent. So this is going to be minus 3 over 2, and then we end up having x raised to 3 over 2 minus 4. And we know that 4 is the same as 8 over a 2. And then this is going to be equal to minus 3 over 2 x. 3 minus 8 is going to be minus 5, and then over 2. So this is what we are actually getting now. So that's the final answer that we have. Let's go back, because we're given is still fine, because one was actually in a normal exponent and the other was in a root, so we're still fine. But you want to change it into a root, you can always rewrite it as minus 3 over 2, and then you have this is actually, because the exponent is still negative, so we'll end up having minus 3 divided by 2 x raised to 5 over 2, which is just the same as minus 3 divided by 2 times square root of x raised to 5. So it would be something of this nature. That's how you would end up solving this particular problem here. Now, when it actually comes to this, so we are actually having now, this is the whole thing. Of course, the first thing that you do, this is going to be h of x, and the denominator is going to be your g of x, and f prime of x is not going to be hard because we know that h prime of x is always going to be low, which means the denominator. So we end up having x squared plus 2x d high. So we are looking for the derivative of the numerator, which is x squared plus square root of x minus low d high minus high, which is the numerator x squared plus square root of x, and then d dx of, I'm going to have the derivative of the denominator plus 2x. So what is important here is that in the denominator, you're always just gonna square the denominator as it is. So the formula is very simple. Low d high, so you have this one's the denominator, low d high minus high d low, low is the denominator. So we always subtract the part that has the derivative of the denominator, subtract the part that has the derivative of the denominator. And then of course this is going to be x squared plus 2x. There's nothing to be done there. But when it comes to this, what is the derivative? We're going to take the derivative of this. You bring the exponent down, so you have a 2 times x, and then you subtract a 1. So 2 minus 1 is still going to be a 1. Still going to be just 1. And then plus the derivative of this, we take note that square root of x is the same as x raised to 1 over 2. So I'm going to bring down a 1 over 2, and then I'm going to have an x, and then I have 1 over 2 minus 1 minus. And then when it comes to this one here, I end up having x squared plus the square root of x. And then when it comes to that one here, I'm bringing the exponent down, and then I'm subtracting a 1, so I'll end up having a 1 plus. I bring the exponent, I have a 1 here. So if I have a 1 here, which means that when I'm bringing in a 1, 1 times 2 is still a 2. When I'm subtracting a 1, I will x raised to a 0. So since I have x raised to 0, x raised to 0 is still just a 1. So I end up having something of this nature. And then I divide this by x squared plus 2x. And then I square it up. So what is important here is this. Let me first simplify a little bit. X squared plus 2x. And then here I will end up having 2x plus, and then in this part here I will end up having 1 over 2 x raised to minus 1 over 2, and then minus, and then here I will have x squared plus square root of x, and then I have 2x plus a 2. And then I divide this whole thing by x squared plus 2x, and then I square it up. Now if you look carefully into this, you will find out that we are trying to make sure that we get something here. We still have x squared plus 2x, and this one want to rewrite it in a form that it was given with. So we have this one is going to be plus. Having a negative here, it means this x is in the denominator, and 1 over 2 is just the square root. So we end up having 1 divided by 2 square root x. And then minus, here I still have x squared plus square root x. And then here we have 2x plus a 2. And then I divide this whole thing by x squared plus 2x, and then I square it up. The reason I'm not simplifying further here is because I don't see the common factor between this one, this part here, and that part. And at the same time, I am not seeing a common factor between this one and both these. So The only way you can continue here is when you are trying to actually expand this whole thing. For me, I'm just gonna stop in here because I don't see the common factor there. Let us look now at the last few things. So I'm gonna give you this one here. I'm gonna call it number 2. The question is, find f prime of u, where I'm gonna have my a here. I have f of u is equal to u squared plus 2u. If I want to find f prime of u here, I have to notice that just because there is no x, it doesn't mean I cannot find the derivative. This is simply saying that actually u is the independent variable, so I'm going to differentiate with respect to u. So this is going to be du, because the independent variable is going to be u there, and then you're gonna have u squared plus 2u. You get what I mean? Just because there is no x, it doesn't mean we cannot differentiate with respect to u. So we differentiate with respect to u because the variable that is inside is actually our u. And then of course, what is the derivative of this with respect to u? You bring the exponent down and you have a u, and then you subtract a 1 from the exponent, plus the derivative of this, there is a 1 there, so I bring the 1 down. The constant is always pulled out, so I bring the constant down, and then this constant will find in a 2, so 2 times 1 is going to be a 2 times u raised to 1 minus 1. And of course, this is going to be 2u because 2 minus 1 is just a 1. And then here, this is going to be u raised to 0. U raised to 0 is 1, so we end up having a 2 there. So this is actually the derivative. The second one here is saying that I have my f of u. F of u is actually equal to u squared plus x times u. So if I want u prime of u, f prime of u, I want to actually take the derivative with respect to u of u squared plus x times u. And I want you to notice something here. This is u, so I can take the derivative with respect to u. And of course, you bring the exponent down, and then you subtract 1 from the exponent, plus. If you look at this x here, this x here, because we are differentiating with respect to u, this x here is actually a constant in this particular case because the independent variable for this function is u. So x is a constant. So you can always pull the constant out and take the derivative with respect to u of what is remaining. That's why I'm giving you these examples, just to boost something so that you can understand that when we are having the independent variable u, then our x here is supposed to be a constant. Hence, this one is going to be 2u plus x. Take a note here that the constant was 2. I've just changed it to some x here because we are using u as an independent variable, which means our x is going to be a constant in this particular case. Let's take also another example here. Our another example will be something like, we have our f of u, and f of u is 3 times u to the power 4 plus 2x. Now, to find f prime of u, all we need to do, we need to take the derivative with respect to u of 3u to the power 4 plus 2x. This is a plus. And if you are doing that, we know that we can take the derivative of this first with respect to u of 3u to the power 4, and then plus the derivative with respect to u of 2x. And if you look carefully into this part here, I want you to notice that I can always pull the constant du, and then I will be left with u to the power 4 plus, and then here I still have du. We'll talk about it in a moment. If you are actually taking the derivative of this, of course, I bring the exponent down, so I have 3 times 4 times u to the power 4, and then I subtract a 1 there. And then in this particular example here is that this one here, there is no u here, and I'm differentiating with respect to u. So because there is no u here, x is a constant, 2 is a constant, so this whole thing here is actually a constant. So because this is a constant, the derivative of a constant is going to be a 0, because in this particular case here, x is a constant. So this is supposed to be 0, and now we're left with 3 times 4 is going to be a 12 u raised to 3. So that's what I wanted you to actually find out, because both of these are constant. But how does a variable become a constant? I mean, because in this particular case, we have our f of means whatever is inside here is actually the independent variable. So if it's not what is inside, then this x here is just saying this is just a constant. This x is a variable, but whatever that variable is, it does not depend on you, so it is a constant. I want you to get to understand this whole thing, that we have this x as a constant. So that's what is important. If you grasp this, you will not struggle with implicit differentiation, because that's what is important when you are dealing with implicit differentiation. So that will be all for now. And then the next thing that we'll do in our next lesson will be actually the chain rule. So we'll talk about the chain rule in the next lesson. The chain rule is simply saying, if I have my h of x, and my h of x is actually the composite function of g and f. We know that the composite function is the same as f of, I take x and I plug it inside here, and then I plug that g of x. Can we actually find the derivative with respect to x of h of x of this particular function? That is actually what the chain rule is all about. And if you understand the chain rule, in other words, you understand the composite functions, you will actually not struggle when we are dealing with the u substitution, when we are dealing with integration. But if you are not good with this, you might actually struggle, because you will not understand what is actually going on when we are undoing something that you are not even good at. So make sure that you actually take a look into that lesson of the chain rule, and make sure that you actually get to understand it deeply, because chain rule is way more powerful, even more powerful than the quotient rule. If you notice here is that you will notice that the combination of the product rule and the chain rule can actually solve problems of the quotient rule. And also the once you are good with the product rule and the quotient and the chain rule, you don't really need much of the quotient rule. But it doesn't mean that you shouldn't study quotient rule, because in most cases when you're dealing with multiple choice questions, all these things that I was saying here, that where's this now? The quotient rule is of this type here. Is most cases you will usually find it in the multiple choice, and the product rule, having this, you will find it usually in the multiple choice questions, and the difference rule, the sum rule, all these things, they are usually there in the multiple choice questions. So as much as I'm just writing them up, and you need to understand, try and understand them one by one and keep them in your head, because we don't usually have a formula sheet when you are writing the tests and the exams in this course. Hopefully you understood what we're actually doing here, and I will stop right there.